so today we're going to look at section 1.1. It's a lot of different topics, small topics, but I think mostly things you've all seen before. So as I go through, I'm going to describe these different number systems. I don't have a definition written out for everything, so if there's something I say and you're not sure, like, wait, what's a whole number again? You might want to write it down. Okay. So we're going to start out with the innermost box, which is counting numbers. So counting numbers start at 1, and they go up. 1, 2, 3, 4. No negatives, no zeros, no fractions, no decimals. Now, the problem is, why don't we just stick with counting numbers for everything? Why would there ever be a need for something more than numbers like 1, 2, 3, 4? Yeah,
in larger scale situations where you have to like count something that's like in thousands or millions or something, it would be inconvenient to have to go 1, 2, 3.
Okay, but like at 1007 is still a counting number. So, or 2,657, that's still a counting number. So my question is, is there any other kind of numbers that we might need that are not counting numbers? Like why are counting numbers not sufficient to do everything we would ever have to do in math? Yeah, Emma?
Maybe like if it's relating to like science or like some sort of like engineering.
Okay, so what would be an example where you might need something besides a counting number?
Well, in physics, there's other numbers.
Like,
Physics is a type of science.
Can you give me an example?
She just gave us one. I forget. Sorry.
Yeah, Lucas?
Gravity,
Okay, what about gravity?
the formula,
Okay,
you can't just express that with a counting number
why?
because that uses exponents and variables,
And variables?
like wind resistance, all that stuff.
Okay, how do you represent wind resistance? Like very generally, what is it in the formula? It's yeah.
I think Earth's gravity is like 9.02 or something like that.
Is that a counting number?
No, it's a decimal.
It has a decimal. Okay, so there are certain kinds of calculations we might do, certain constants we might need that are not counting numbers. Anything with a decimal wouldn't be able to work with a counting number. Even more basic, let's just talk about addition. Okay, we'll start nice and simple. Let's say in that box, you pick a counting number. And then in that box, you pick another counting number. The question I have is, what ends up in that box, will it also be a counting number? Okay, so let's try an example. Could somebody give me a counting number? Any counting number?
6.
6. And how about another one?
27.
27. I'm not interested in what 6 plus 27 is. I'm interested if the answer is a counting number. So if you add 6 and 27, do you get a counting number? Yeah, you do. So in fact, if you add any counting number to any counting number, you will always get a counting number. That's called closure. Okay? Whenever you add two numbers from the same set, and the answer that you get is also in that set, that's called closure. With addition, that always works. Let's just go like this. Let's make it subtraction. 6 minus 27. 6 is a counting number. 27 is a counting number. How about 6 minus 27? Is that a counting number? No, that's not a counting number. So when you are doing subtraction with counting numbers, it is not necessarily closed. That means you can get an answer that doesn't fit in this box when you do subtraction. That's a problem. Okay? If it doesn't fit in that box, then that means you either do one of two things. You have to say undefined, because you have no way to represent it, or you have to expand the type of numbers that you work with so there is a way to represent it. And that's what this chart does. So the next type of numbers is whole numbers. Whole numbers expands counting numbers by one number. It adds just one more number into the set. It adds in 0. And you might think, well, isn't 0 just always around, always a thing? No, think of Roman numerals. What's the Roman numeral symbol for 0? There isn't one. They didn't use 0. Smallest Roman numeral is I. It's a 1. Okay, so they didn't really think about the concept of 0. It's just something they didn't use, didn't need. But if you had a subtraction problem like that, you certainly need the number 0. So whole numbers give us a little bit more to work with. They give us 0. Well, we could still run into problems like this one. Whole numbers don't solve this problem. 6 minus 27. That gives us a number that is not a whole number, so we expand our numbers to include integers. Integers include positives, negatives, and 0. So integers are like -3, -2, -1, 0, 1, 2, 3. Okay, continue forever in each direction. No fractions, no decimals. So now, let's think about integers. If you add, again, now we're thinking about integers. If you add an integer to an integer, will you always get an integer? Yeah, that's fine. How about if you subtract an integer minus an integer, will you always get an integer? No. So subtraction is closed under integers. And when you start with an integer, you end with an integer. How about multiplication? If you multiply an integer times an integer, will you always get an integer? Yep. So multiplication is also closed. Now let's talk about division. We can use that example right there. 6 divided by 27. 6 is an integer. 27 is an integer. Is the answer an integer? No. So now one of two things. You either say you can't do it, it's undefined, or you expand the kind of numbers you're allowed to work with. And the next set we extend to are rationals. So rational numbers basically include all your fractions. So to write a rational number, it has a numerator and a denominator. Denominator can't be 0. And both the numerator and the denominator have to be integers. So when you write a fraction, you really shouldn't do something like this. It's kind of a weird way to write a fraction. If you want to write that as a fraction, then you should write this. 35 over 74. That's how you write it. So now with rational numbers, you've got all your fractions, you've got all your decimals, positives, negatives, and 0. But in math, there's still calculations we could do that might end up where we start with a rational number, we do something to it, and the answer isn't rational anymore. Does anybody know something you can do to a number and it could become irrational? It's something besides add, subtract, multiply, and divide, but it's still a relatively basic operation.
Square root?
Yep, square root. So start with a rational number. 3. Okay, take the square root of it. Square root of 3 is now irrational. You would never be able to write that as a fraction. And square roots come up a lot of times when you're working with quadratics. If you're solving a quadratic equation, the answer might have a square root in it. If you are doing Pythagorean theorem or distance formula, the answer might have a square root in it. So rational numbers are all the numbers you can write as fractions. Irrational are the ones you cannot. When you put all those numbers together, rational and irrational, that's the real numbering system. And for now, that's what we're going to stick with. Okay. There are numbers beyond reals. We'll talk about imaginary, but not right now. And if you think of these as places, like think of the innermost box as like a smallest place, and as we work our way out, we get bigger. So think of like Boston, Massachusetts, New England, United States, Earth. Okay. If you are in Boston, are you automatically in Massachusetts? Yeah, that works. If you're in Massachusetts, are you automatically in Boston? No. So if you are a counting number, you are automatically a whole number. But if you're a whole number, you're not automatically a counting number. Okay, so just think of it like the places. If you're on Earth, are you automatically in Boston? No. But if you're in Boston, then yes, you're automatically on Earth. Okay. All right, so any questions on the different number sets? Now, some of the number sets we have symbols for. So Z stands for integers, Q for rational, R for real. Not sure the Z, where that one comes from. Q might be quotient. When you think of fractions, rational. Now, you can also write something like this. What do you think that symbol means? Jacob, do you have an idea what that symbol might mean? Do you know what it might have something to do with?
Maybe like positive?
Positives, yeah. Can you be it's a little more specific?
Not too sure.
You want to help them out? Something to do with positives, but a little more specific than just positives. Yeah.
Positive real numbers?
Positive real numbers, yeah. So that symbol would mean positive real numbers. You could put a little minus there if you wanted to say I'm talking about negative real numbers. And you could do the same thing with the other symbols as well. So any question on those three symbols? Those are the only ones. Counting numbers don't really have a symbol. Whole numbers, not a well-known symbol that I'm aware of, but those three do. Okay, so when we were checking for that property of closure, whether you start with something and you end with the same type of number, we were checking it with these different operations. Okay, those are called binary operations. The reason they're binary is because to do addition, you need 2. Right? Square root is not a binary operation. You don't plug in 2 different numbers. If I want you to take the square root, you just plug in one number. Square root of 7. Just one number. So we're going to look at some other properties, and I'm going to write down the closure again as well. But we're going to look at some properties, and I'm going to need to use some variables to represent these properties. The variables A, B, and C will represent any real numbers. Now let's think about addition. If I start with a real number and I add another real number, do you think I will get a real number? Is the answer. What do you think? Is a real plus a real always going to give you a real? Yeah. So that's called, again, closure. The idea that you can add 2 numbers together from a set, and the answer you get is in the same set. Pretty much every operation all the binary operations work for closure. Add, subtract, multiply, and divide. All of them. Square root does not. You take the square root of -2. -2 is a real number. So you start with a real number. Take the square root of it. Square root of -2 is imaginary. So that would be a little different. How about, does anybody remember, let's do it this way, this top property. where you can switch the order and you still get the same answer. Anybody remember that one?
Reflexive property football.
Reflexive has to do with having the exact same thing on each side of an equation, like a plus b equals a plus b. It's like identical. This is a little different because the order switched. But that is a property we're going to mention in a little bit. Anybody remember the name of that one? Not sure, it begins with a C. Help anybody? Think about when like you go from your house to your work. Like you do that over and over. You call that something. Where you go from point A to point B every day. It's your daily, commutative, yes. So commutative is when things go back and forth. They change, it's like you change places. So that's the commutative property. How about this one? The order is ABC, ABC. It's the same order on each side, but I've changed the grouping. Anybody remember what that one's called? Change the grouping. If you think of like your group of friends, you could say, well, it's it's the group of people I hang out with, or you could say that's the people that I can't. It begins with an A. It's like the people that you talk with, you hang out with, associative. It's like who you associate with. So parentheses basically group the B and the C together in the first case, and the A and the B in the second, but it doesn't matter. You're going to get the same result. Okay, next one, let's do it this way. Identity property. Identity is an operation you can do to a number and get the same number back. What could you do with addition that gives you the same answer back you started with? Emma?
0.
Yeah, you could. What would 0? Multiply by 0?
Any.
Well, if you multiply by 0, you're not guaranteed to get the same number back.
Oh.
You might in
plus-
one
plus
case.
0.
Plus 0, yeah.
Or minus.
Yeah, it must be 0 plus 0, yep. So identity property for addition is add 0. Identity for multiplication is multiply by 1. So a lot of these properties can apply to multiplication and addition. The inverse property, that one's a little tricky to remember what it's called. It's a simple idea. If you add opposites, you get 0. So the inverse property of addition is something you can basically do to inverse or cancel out a number and get 0. You do it all the time when you have something like this. To solve that, you would do the inverse of 3 on each side, which is subtract 3. Okay, and distributive, well, that has to do with having parentheses and multiplying. Now, this is what we call pre-multiplication, because the A comes before. You can write distributive property like this. A lot of people don't. But you could put the A after, and that means the same thing. That's called post-multiplication with distributive property. Now, I told you that a lot of those properties also apply for multiplication. There's no distributive property when you have multiplication inside here. You definitely don't do that. Like if you had 2 times 3 times 4, you never distribute 2 times 3 and 2 times 4. That's not how you do distributive property. So distributive property only works for plus or minus. But identity property works for multiplication. Associative works, commutative works, closure works. Those all work. Okay, and those are all on page 2 in the textbook. Okay, so a lot of the things we just wrote down were expressions, right? A times B, A plus B, things like that. Now I want to extend that to an equation. To make something an equation, What symbol do you think has to be? Yeah, go ahead. Now,
Equals sign.
an equal sign. You can have an equal sign. So those are all examples of equations. All of them. Top one is what we call a conditional equation, because if you pick the right value, if you have the right condition for x, it will be true. The bottom one, well, if you simplify it, what does the bottom one basically say? Well, E. What does the bottom one say?
7 equals 7.
7 equals 7. That's called an identity. An identity is when you have the same thing on the left and on the right in an equation. And this last one over here, it is an equation. It's not true. It's a contradiction. So conditional, identity, contradiction. Now I said an equation is when you have an equal sign between two expressions. Expressions can be algebraic or numeric. That's an algebraic expression because it has a variable. That's numeric because it does not. So that's an algebraic expression and a numeric expression. That's a numeric and a numeric. That's fine too. You just need two expressions and an equal sign. Okay, so now that we've talked about equations, there's three other properties we can look at for equations. And I'm going to use the letters A, B, and C. The first property somebody already mentioned. Reflexive is when you have exactly the same thing on the left and on the right. You see that sometimes when you're doing proofs, like you're proving triangles congruent, like side AB is congruent to side AB. That's like the reflexive property. Okay. Symmetric. Symmetric is, it's kind of like commutative property, but you're actually switching what's on each side. Okay. To be commutative property, it has to be on the same side. That's an example of commutative, because I took A plus B and I turned it into B plus A. I just switched these two things on the same side. Symmetric, you're switching the entire side. And the last one is transitive. Does anybody remember what the transitive property is? Yep, Lucas.
If A equals B and B equals C, A equals C.
Yep, I kind of remember that. It's like when you have a chain of things. You can have 3 things, 5 things in the chain, but yeah, that's exactly it. Okay. Any questions on those 3 properties? Okay. So what I want to do here is identify some of those properties that I just gave you. Okay, I'm going to do it a little different than I did in the first class. I'm going to do out the step, and I want you to tell me the name of the property I used. Okay, I'm going to start with this. So under that box is the name of the step that I just did. Anybody remember looking at what I did, the name of the property that I just used? Yep, go ahead, Davis.
Distributive.
Yep, that's distributive property. Perfect. Now this one doesn't really have a good name. I'm just going to do this. Don't overthink that too much. But what did I basically do in that step? Yeah. I didn't switch the order. Like if this said 2x plus 6 on that side, then I would have switched the order. I didn't really change the order of anything. Yeah?
Multiplication?
Yeah, I just multiplied it out. I simplified it. That's all I really did. Nothing changed with order. I just turned 2 times 3 into 6. That's it. Now, in order for what's on the left and on the right to be the same, they should be in the same order. left side stayed the same, but I did something on the right. What property did I just use there? Yeah.
Identification.
So identity would have been if I had something like 3 plus 0, and then in the next step I said, well, that just equals 3. You get back the same thing you started with. So adding 0 is usually the hint that it's the identity property. But there's no, I didn't really add 0 there. Yep.
Now is it commutative?
That's commutative. Yep. I took these two on the same side of the equal sign, and I switched the order. Yep. So you may be given a problem where I show you the steps and you tell me the name, or I'll reverse it and say, here's the properties, show me what it would mean to do that step. Any questions on that? All right. Okay, done with properties. So now, next part of the lesson. Okay, coordinate system. So not even 2D coordinate, just 1D, so number line. Positive numbers go to the right, negatives left, and the middle of the number line where we put 0, that is the order. Now, once you draw a number line, that allows you to do something like this. There's an order. If I compare where the green dot is to the black dot, it is to the left of it. That means something. The red dot is to the right of the black one. That means something else. There's 4 different symbols we can use to describe the relationship between two numbers and how they relate to each other on a number line. Does anybody know the 4 symbols I'm thinking of? Yeah, 8.
Greater than, less than, greater than, equal to, and less than equal to.
Yep, those are the 4 symbols we can use to describe the order of how two numbers compare to each other. Now, these 4 symbols all together have a name. Does anybody know what we call those 4 symbols as a group, Dave?
Inequalities.
Inequalities, yep. Those are your 4 inequality symbols. And a lot of times when we are solving a problem and we end up with something like this, x is greater than or equal to 7, we might not want to write the answer as an inequality. We might want to write it or sketch it. I might say sketch the solution, graph it. In order to graph an inequality, first thing we're going to need is a number line. So we've got a number line. And we're going to have to put a circle on the number 7. There's 2 kinds of circles. Does anybody know the 2 kinds that I'm referring to? Yeah, Claire?
The empty circle means it's not equal to, and the circle still means it is equal to.
Yep. So the 2 kinds of circles, you get the open and closed. And if you keep it open, that means you had a greater than or a less than. Or like in this case, it should be a closed circle because it's greater than or equal to or less than or equal to. So if I was going to graph this, I'd put a closed circle on the 7. And there's one more thing I have to do after I put that closed circle. You just put the circle, that's x equals 7. But I want everything equal and higher. So I got to indicate the higher.
Draw a line defining what values x could be.
Yep. So we'd want to put an arrow, and we would shade to the right. So that's the last step. You need to shade. Now, are both of those the same thing? This and that. Yeah, they're the same thing. So technically, I would mark either one of those correct, but I do prefer one over the other. Which one do you think I would prefer? Yeah.
The one with the x first?
Yeah, the one with the x first, the variable first, because if you put the variable first, this symbol tells you which way to shade. If you don't put the variable first, then this symbol tells you the opposite way to shade, and that gets confusing. So what kind of circle would we need on 2 in this case? Yep.
Close.
We need a closed circle. And we're shading everything that's 2 or higher. Okay, and that's pointing to the right in this example. So we shade to the right. How about this one? Are those the same thing? Let's start with that. Yeah, they're the same thing. But again, I prefer the one that we said earlier with the variable first, because then it tells you which way to shade. Okay. What kind of circle do we need on 3? Open or closed? Yeah. Open. And from that circle, I need to shade everything that is smaller than 3. So we can shade that way. Okay, so any question on using open circle or closed circle? Because another way you can do it is to use an alternative symbol, and this is what we'll see in our book. I'm going to stick with the circles mostly when you got to do it on like pair assessment. It's a circle. But if you see a bracket, our book uses a bracket instead of a closed circle. It works exactly the same way. Only thing you have to think about beforehand is there's 2 different brackets. The bracket has to face the way you want to shade. All right. So if I was doing this one, I would put a bracket just like that on the number 2, and then I would shade to the right. And the reason it's kind of a good idea to start thinking about it in terms of a bracket is because eventually this is one way to write an answer. That's called an inequality. This is a second way to write an answer. That's called a graph. The third way to write this answer would be like this. That is called set notation. Has anybody seen that before? A couple people? Okay. Set notation is what we're going to use quite a bit. Maybe you kind of understand what I'm doing there. Maybe not. But the fact that that's a bracket and it's on the 2, and that's a bracket and it's on the 2, those ideas are connected. Now, we use a bracket in place of a closed circle. What symbol do you think we would use for an open circle in our book? Yep.
Parenthesis.
Yep, parenthesis. So if I was going to graph this one, I need a parenthesis on the 3, and I'm shading everything smaller than 3. That is how you would represent this inequality as a graph. And if you'd want to see it as a set notation, it would look like that. Okay, I'm just showing it to you. I want you to kind of just start to get used to seeing it. We're not really studying it yet. But this means from negative infinity up to not including the number 3. And whenever you see an infinity in a set, it means that it goes on forever. And that's what an arrow indicates, goes on forever. Now, this is a compound inequality, and it's pronounced using the word and. In fact, the way you pronounce it is just like that. I usually start and I read from the middle. X is greater than or equal to 2, and x is less than or equal to 9. So if we want to graph something like that, we need 2 circles or brackets, parentheses, however you want to do it. Let's use circles. The first number is a 2. Based on the symbol, what kind of circle would we put on the 2? Yeah, I do.
Closed.
Closed circle. And what kind of circle would we put on the 9? Okay.
Close.
Closed. Now, where would I shade? This isn't going to have an arrow. This is different. Yeah.
Shading between.
You shade in between. Perfect. So that's a conjunction. Now, what if I had, let's say, x is greater than or equal to 4, and x is less than 12. I want to combine that together. So it looks more like this. What do you think would go in the middle? Yeah?
X.
The x. Yep. Now, you have two choices. You either put the low number on the left, which is how I do it, or you put it on the right. Let's put the low number on the left, which means what number is going to go on the right? Yep. 12. What inequality symbol would I put between the 4 and the x so it's equivalent to that? Be careful, because the x is in the middle. It's not. Yeah?
Less than or equal to.
Right. And that symbol, when you look at the x and the 4, it's pointing at the 4. Pointing at the 4. Yep. And what symbol would I put between the x and the 12? Yeah.
Less than.
Less than. 8, right? Yeah. So that's how you can take 2 and combine them. Okay. So you should be comfortable with combining 2 into 1 or splitting 1 into 2 for inequalities. That's the only word you can shorten up. Like you can take an and shorten it. If it was an or, there's no short notation like this for an or. You just have to write first inequality or second inequality. You've got to write the word or. Okay. Any question on that? Okay, so next topic, absolute value. What is absolute value? I just want to say, there's different ways to talk about it. I just want to see what people tell me. Yep.
The distance on the number line from that number to 0.
Yep, so that's a very geometric way to think about it. Looking at how far apart two things are and measuring the distance. Yep. Now, when you measure a distance, what kind of number would you never get when you're measuring distance? Never get a negative. Okay. Could get 0, but you'll never get a negative. Now, that's the way most people kind of think of it right away, distance from 0 on a number line. But there's really two cases. So let's pretend like I'm a computer. Okay? And you're going to tell me a number, and I'm going to give you back the absolute value. If you give me a number that's 0 or higher, what would I give you back? The what?
Same number.
I'd give you back the same number. If you give me a number 0 or higher, I just tell you the same thing back. That's the absolute value. So you give me 5, I give you 5. You give me 12 and a half, I give you 12 and a half. I just give you the same number back. Now, what do I have to do in my head if you give me a number that's not greater than or equal to 0? If you give me a number smaller than 0, what do I have to do to the number before I give it back to you? Yeah?
Make it the inverse.
All right, how do I do that? Can you explain like a calculation I could do in my head to make that happen? I don't know inverse. I know add, subtract, multiply, and divide though. Yeah?
Times it by -1.
Exactly, times it by -1. So that's formally how you could define absolute value. If you give me a number less than 0, I will times it by -1 and then give it back to you. If you give me a number that's already 0 or higher, I'll just give you back the same number you gave me. That's kind of a very formal definition of absolute value without thinking about distance on a number line at all. Okay. So 2 quick examples. Absolute value of 6. Just give you back the same number. Absolute value of -3.
3.
Multiply it by -1 because I got to get rid of the negative, and I get 3. Okay. Now, what can we do with absolute value in a number line? We can find out how far apart 2 points are. If you've got a number line you've got a spot here and a spot here. And you want to know the distance between the two. You can subtract a minus b and then take the absolute value. But what if I did this? How would that compare to what's up above? Yep.
It should be the same, right?
I thought when you subtracted, though, I said earlier subtraction didn't apply to commutative.
Yeah, but when you, hold on, I'm blanking on the words, but basically, when you, I'm sorry.
Anyone help them out? Yeah?
Commutative is not the same with subtraction because it would be the inverse or negative version of a positive. If the answer is positive, it would be negative. If it's negative, it would be positive instead. But absolute value is positive either way.
Right, the absolute value is going to cancel out any negative sign. So yes, when you subtract something in the opposite order, you get the opposite, but absolute value negates that. Okay, so technically you could find the distance between two things either way. So if I wanted to find the distance between -2 and -9, think of -2 as A. Think of -9 as B. And plug those into your formula. Now, if you're going to simplify that, think of your absolute value bars as like parentheses. You're going to do what's inside first. What's going to happen inside when you do -2 minus -9? Yeah.
The double negative turns into a positive.
Yeah, so that's going to become a positive. And -2 plus 9 is going to give me how much? 7. And the absolute value of 7 is 7. So the distance between -2 and -9 is 7. Okay. Any questions on that? So next thing, let's take our number line and extend it to 2 dimensions. When we do number lines in 2 directions, we call them axes. And we have a name for the horizontal and the vertical. What's the name of the horizontal axis? It can be many names, but the most common name. Yeah.
The x-axis.
X-axis. And the vertical?
Y-axis.
Y-axis. And where the x and the y-axis cross? Yeah. Origin. And if you take a piece of paper and draw an x and a y-axis, it separates it into 4 regions, which we call quadrants. Yep. And how do you specify a specific location in a quadrant? What do you use? Yep. You use an ordered pair. Yep. Exactly. So I think that covers everything we just said. Oh, except the numbering. Quadrants are numbered 1, 2, 3, 4, starting in the upper right, and they go counterclockwise. And if you want to specify a specific location, like this point right here, you use what's called a coordinate, or the specific kind of coordinate in 2 dimensions. It's called an ordered pair. In 3 dimensions, you call it an ordered triple. What I'm showing in parentheses is that in quadrant 1, the x and the y value are both positive numbers. In quadrant 2, x is negative and the y is positive. Okay, when you write a coordinate, the order matters. It's got to be x then y. If you switch it, it's not the same coordinate. Okay. Any question on 2D coordinate system? Okay. So this might be the thing that's new for today. So what I want to do now is bring up our calculator. Okay. If it's not on, if yours has black screen like that, I'm going to press on. And the button in the upper left says y equals. Okay, all the way in the upper left, I think it's yellow on yours, if you're using one of my calculators. I want to press that y equals button. Now, there's already something typed in on mine. I want to get rid of that because we're going to do something else. I'm going to press clear. If there's ever anything typed in, you can just press the up or down arrow until you get to that line and press clear. Does everybody's screen look exactly like that with y1 through y9 on the left and nothing typed in on the right? All right, so what I want to type in is x squared minus 10. To type in an x, it's the button right below mode, and it's to the right of alpha. In fact, it has like 4 different letters on it, but the first one says x. So you're going to press in x. And I said I want to do squared. So let's do x squared. Squared button is the 5th button down on the left-hand side. Does everybody have x squared typed in? Okay. And let's do plus 15. So we do x squared plus 15. All right. Now I want to graph that. Before you graph anything, you always want to either use the window or the zoom button. Okay? What that's going to do is it's going to allow us to set how big the x-axis is and how big the y-axis is. It's like how big the graph paper is. The standard window that we always generally start with is -10 to +10 on the x and -10 to +10 on the y. If you press zoom, and then you can either go down to the 6 and hit enter, or just press 6. Zoom, 6. It automatically just set it -10 to 10 and -10 to 10. And there was a yellow circle spinning in the upper right. While that circle was spinning, it was drawing the graph. Where's the graph? Yep,
Off the screen.
it's off the screen. Okay, that's one of the hard things with using the calculator to get used to. Sometimes you have to find where your graph is. This one's not hard to find. It's not that far off the screen. But your graph could be hundreds of units off the screen. Okay, thousands. So sometimes you have to find it. Does anybody know that's a quadratic, but the name of the shape when you draw a quadratic? Anybody remember what that's called? Yeah? It's a parabola. This specifically is a parabola shifted up 15. When you graph something, you have to kind of know what it is you're graphing, so you have an expectation in your head of what it's supposed to look like. And you have to know that this plus 15 is a vertical shift up 15 units. So I know with that information, a standard window is not going to work. So what we have to do is fix it. Okay. What I want you to do is, instead of pressing zoom, press window. If the graph was shifted up 15 units, you're going to have to adjust one number to see it. It's either xmin, xmax, ymin, or ymax. Anybody have an idea if it was shifted up, which number we want to make higher? Yeah?
Ymax?
Ymax. What do you think a good number to try would be?
20.
20. Let's try 20. So I'm going to change Ymax to 20. And I'm going to hit graph again. Don't do zoom 6. If you do zoom 6, it's going to go right back to -10 to 10. 20 worked. Okay, I can see my parabola, and now you should have a picture on your screen as well. How many people got a picture that looked exactly like that? Okay. Anyone that didn't get a picture of a parabola? Did you get it? Let's take a look and see. Oh yeah, so yours is different. We gotta just change that back. Now, so now you got it all typed in, but you might have to set the Ymax higher. Now, you might just say, well, why don't I just set the Ymax to like 10,000? Okay, well, the problem with that is, if you set the Ymax that high, you are now zoomed out so far, I can barely even tell that that curves. Right? So it's kind of a balance between a number that's too high, but a number that's not high enough. So even a number like 50, that'll look fine. You'll definitely be able to see that's a parabola. That's it. Okay, so that's how you can adjust your window. And that's one of the most important things you have to do when you're graphing. Because if you can't see what you're graphing, you're not going to be able to figure out how to solve the problem. Because your screen will be blank. All right, so I think the question here was to set your window from -20 to 20 and -20 to 20. I want you to understand what those four numbers mean. When they write something like this, first of all, in the homework, you'll have a question like that. There's nothing to show on paper. This is purely a question you do on the calculator. So on your homework, you would just write, I set the window on the calculator. But the first number they give you are always the x's. First, the min, then the max. The second pair of numbers they give you are the y's. The min and the max. And those are really the only four numbers you'll ever need to set. If you notice, there are other numbers, like the scale. The x scale is, if you don't like the number of tick marks on the screen, you don't want one every unit, you want a tick mark every 2 units. Okay, we can space the tick marks out more. But never will really be doing that, so you don't need to worry about it. So any question on, well, we didn't actually type it in, but if you want to type those in, you press Window and change all the numbers. -20, 20, and so on. You just type them all in. And now my parabola looks a little different. I didn't change the shape of the parabola. It's the same equation. But I changed the size of the screen, so yes, that distorts it. It's like imagine writing on a rubber band, and then you pull it. Well, you didn't change what was written on it, but you changed the screen you're using to look at it, so it distorts it. Okay, any questions on that? All right. And last thing. So the last thing we're going to look at is the distance formula and the midpoint formula. So distance formula would be used. So you had a point here and a point here. And you want to figure out how far apart those 2 points are. Well, distance on a diagonal is hard to measure. So to use the distance formula, we're actually going to take that and turn that into a shape. And that's going to be one side of my shape. Anybody know what shape I'm going to turn that into? And it's going to help me to measure the distance between those 2 points. Yeah?
Right triangle?
Yeah, we're going to make a right triangle just by drawing in a horizontal and a vertical. And here is your right triangle. Now, why change it to a right triangle? Well, in a right triangle, you end up with something that's perfectly horizontal, and then you end up with something that's vertical. Horizontal distances, very easy to measure on a grid. So are vertical distances. But how would knowing a horizontal and a vertical help me to find a slanted distance? Yep.
Pythagorean theorem.
Right. We use Pythagorean theorem, and that's exactly what that formula is. So this coordinate is x1, y1. And this one is x2, y2. Think about how you find how far apart two things are. We just talked about that. You subtract. So if you want to know the distance from here to there, that's a horizontal distance. You've got to find out how far apart the x's are. this has a point of x1. This one's not labeled, but what's its x value? Even though this isn't labeled, we know the x value of this coordinate. Anyone can tell me? I mean, we don't know it as a number, but we have like a notation for it. Yep.
It's X2.
Yeah, it's x2 because it lines up vertically with this point. And we know that has an x value of x2. So if that's x1 and that's at x2, and you subtract the two, that'll tell you how far apart they are. Same thing for the length of the green. This is y1. It's not labeled, but it lines up with that one. And that's y2. If you subtract y1 minus y2, it'll tell you the length of that green segment. And then we square them because that's part of Pythagorean theorem. So that's our distance formula. So let's see if we can find the distance between those 2 points. So when we fill them in, we're going to start with the square root of x1 minus x2. What's x1 minus x2? -4. And then square it, you guessed, 16. y1 minus y2. What's y1 minus y2? Yeah.
-1.
So y1 is how much?
Oh, never mind. Sorry, I was looking at the wrong thing. -2.
-2. And then when you square it?
4.
4. So the distance is the square root of 20. But we always want to reduce square roots if we can. What is the square root of 20 reduced to? Yep.
2 root 5.
Yep, 2 root 5. So very important we know how to do that from algebra. And that's the distance between the 2 points. All right, so last formula, this one's even easier because it doesn't have a square root, is midpoint. Midpoint basically tells you the halfway point. So if you've got a line segment, it tells you where the middle is. Now, if you look at the formula, you're adding up the x's and dividing by 2. What's the name for that kind of calculation? When you add two things together and divide by 2? It's really just what?
Average.
Just the average, yeah. So the midpoint is the average of the x's, add two things and divide by 2, and then the average of the y's. That's all the midpoint formula is. It's 2 averages. So let's finish up with the midpoint between -5, 2 and 3, 7. So we're going to start with the x's, add them up, and divide by 2. What's -5 plus 3? -2, and then divide by 2. Yeah,
-1.
-1. Okay, so that's the average of the x's. And how about the average of the y's? 2 and 7. Just leave it as a fraction. What is it?
9/2.
Yep, 9/2, or you could do 4.5. But that's the average of the x's and the average of the y's. Okay, so a lot of different topics, but really, hopefully every topic there you had already seen maybe except with zooming in and out or setting the window on a calculator. All right. So that is the homework for tonight. Remember page 11, that's a PDF in Schoology. Make sure that you show your work on the same page so that way you get full credit. If there are any questions that say, you know, set the window on the calculator, well, that's not something you'd show on paper. You could just write, I did it on the calculator. All right, and that's it for our first section.